In this lesson, we'll talk about big idea number 1. How can energy changes be described quantitatively? And we'll discuss learning target number 1. So by the end of the lesson, you should be able to describe the law of conservation of energy and explain why enthalpy changes occur in physical, chemical, and nuclear reactions. Thermodynamics is the study of energy and energy transfer. The first law of thermodynamics is the law of conservation of energy. It states that energy cannot be created or destroyed. Therefore, the energy in the universe is always constant. Energy can only be transferred from one object to another or transformed into a different type of energy. Heat, light, sound, and mass are all different kinds of energy. Mathematically, the first law can be expressed as the change in energy in the universe equals the change in energy of the system plus the change in energy of the surroundings, and that also equals 0. Or, if we rearrange, the change in energy of the system equals the negative change in energy of the surroundings. The system is defined as the part of the universe that's being studied. In chemistry, this usually means the chemical particles involved in a reaction. The surroundings are everything else in the universe, including the beaker, any water your chemical is dissolved in, and yourself. Enthalpy, symbol H, is the total internal energy of a substance at a constant pressure, and it is measured in kilojoules or kilojoules per mole. It takes into account all of the potential and kinetic energy of the particles in the system. Chemists study the enthalpy change of a system that is undergoing a reaction or physical change. We use the mathematical symbol delta H to represent this. Enthalpy changes occur when the type and number of bonds in your chemical system change. Whenever a new bond, including intermolecular forces, is formed, energy is released from the system, creating more stability. Conversely, energy is required to break bonds, therefore the system absorbs energy from the surroundings. This creates two classifications of enthalpy changes. First, exothermic change, when the amount of energy released forming the bonds in the products is greater than the energy required to break the bonds in the reactants. There is a net release of energy to the surroundings. And 2, endothermic change, when the amount of energy required to break the bonds in the reactants is greater than the energy released forming the bonds in the products, there is a net absorption of energy by the system. Below is a visual way to represent an exothermic and an endothermic change. Remember that in every change, old bonds are broken and new bonds are made. The type of enthalpy change is determined by which way the teeter-totter tips, meaning which side has more energy, the reactants or the products. If the reactants have more enthalpy, then the change will be exothermic. If the products have the most enthalpy, then the change will be endothermic. Enthalpy changes can be communicated in 3 different ways by scientists. First, by using a thermochemical equation. It's just a balanced chemical equation which includes energy. If the change is endothermic, energy is a reactant because it's required for the reaction to occur. If it's an exothermic change, you place energy as a product because it is being released. Here are 2 examples. Because I have energy on the reactant side of the equation, forming water is exothermic. But in this example, when I decompose magnesium carbonate, energy is a reactant, meaning that the change is endothermic. Equations are often balanced for 1 mole of the chemical you are interested in. If the equation is balanced differently, then the amount of energy will change. For example, if I take my first equation, forming 1 mole of water, but I balance it so that this fraction is no longer there, I will have to double the amount of energy. I went from forming 1 mole of water to forming 2 moles of water. If you're writing a thermochemical equation, it is okay to leave fractions as coefficients. This is different from what we discussed in grade 10 and 11. The second method used to communicate enthalpy change is by using an enthalpy reaction value. The energy is written after the balanced chemical equation as a delta H value. Endothermic reactions have positive delta H's because energy is entering the system. Exothermic reactions have negative delta H's because energy is leaving the system. Here are the same reactions, but communicated as delta H values. Because forming 1 mole of water is exothermic, it has a delta H naught of minus 285. Because decomposing 1 mole of magnesium carbonate is endothermic, it has a positive delta H value. The little circle is described as a knot, and it means that the reaction was performed at SATP conditions. The third way of communicating an enthalpy change is by using a graph known as an energy diagram. It compares the energy of the reactants and the products. If your reaction is exothermic, then your reactants will be higher energy than your products. And your delta H will have an arrow going in the down direction because energy is leaving the system. If you have a reaction that is endo, then your products will have a higher energy than your reactants, with an arrow indicating your enthalpy change going in the upward direction. The amount of energy released or absorbed by the system is directly related to the amount of chemical used or made. So stoichiometry and mole ratios can be used to determine the actual amounts of energy in particular reactions. Here's an example. Given the following equation and delta H value, is the above reaction endothermic or exothermic? Well, because the delta H value is positive, then the reaction is going to be endothermic. What is the enthalpy change if 5 moles of magnesium carbonate decompose? I like to think of this as solving the equation by using a conversion factor. I have a balanced chemical equation that tells me the ratio of chemical to energy. If I have 5 moles of magnesium carbonate, if I times it by what I want, the energy, I have a delta H value of positive 117.3 kilojoules, and divide that by the coefficient in front of the chemical I'm interested in the balanced chemical equation, my moles of magnesium carbonate cancel out, and I'll end up with my answer in kilojoules. And that will be how much energy gets released when 5 moles of MgCO3 decomposes. Pause the video and try the next example. For example 2, you're given a thermochemical equation. Using this equation, What is the delta H value for this reaction? Well, because the energy is on the product side of the equation, that means that this reaction is exothermic, and therefore my delta H value will be negative. Question B. How much energy is released when 160 grams of calcium chloride is produced? First, I need to figure out how many moles that is by dividing by the molar mass of the compound. To complete the question, I changed my moles into energy by timesing by a conversion factor. I get the 1 mole of CaCl2 because there is no coefficient in front of that chemical in my balanced equation. Question C asks me to draw an energy diagram for this reaction. I would draw a graph with my reactants higher in energy than my products because this is an exothermic reaction. I would draw an arrow going down with my delta H being shown as a negative value.